Okay, so oxidation reduction reactions. And before I get into the details of the example here, let me give you one or two little tricks maybe to help remember what the definitions are here. So one of the ways you can kind of keep track of these is Leo and Ger. So it's usually phrased as Leo the lion says Ger, kind of the growl of a lion. So Leo means losing electrons is oxidation. Ger means gaining electrons is reduction. So that might help you figure out, right, which one you should call oxidation, which one you should call reduction. The other common technique I've heard here is oil rig. And this is very similar. It's oxidation is losing, reduction is gaining. So speaking about electrons. So either of those maybe will give you a good chance of making sure you identify the correct one once you've identified which species lost electrons, which species gained electrons. Now, here's a real simple example, and this is something we might have talked about back when we talked about just the formation of ionic compounds. If we start with just sodium atoms here, we know that atoms have the same number of electrons as protons, so the charge on a sodium atom is 0, right? Because the number of positives and the number of negatives is equal, they kind of cancel out, no net charge. This is the atomic form of chlorine as well. Now these are, or I should say the elemental form of chlorine. This is a molecule, but this is the elemental form, meaning it hasn't lost or gained any electrons yet. So that would also, each chlorine atom in that molecule would have a charge of 0. But over here on the product side, we know once we've made an ionic compound, sodium chloride, an electron has transferred from the sodium metal to the chlorine to make it into the chloride anion. So over here on the product side, the sodium we know has a charge of +1, and the chloride here has a charge of -1. Well, that means electrons have moved. Right? If the sodium goes from 0 to +1, that would mean it lost an electron. So each sodium atom in this equation would have lost an electron. Right? And the chlorines, they go from 0 to -1. That means each chlorine atom gained an electron here in this reaction. And if you think back to our discussion above, losing an electron, that's oxidation. Gaining an electron, that's reduction. So this would be an oxidation reduction reaction, sometimes abbreviated redox reaction. Sodium was oxidized in this reaction, and the chlorine was reduced in the formation of the products. Right? Now, that is a very simple example. It's generally going to be more complicated because a lot of compounds that we've talked about naming molecular covalent compounds, it's not as easy to identify something like a charge like it is for an ionic compound. So there's a set of rules we will follow to identify something similar to charge for elements that are involved in covalent compounds or even that are inside of polyatomic ions, and that is called the oxidation number. So we'll see in the rules that it's related to charge, but it's a little different. So what we want to do is look at any molecular formula that might show up in an equation, identify the oxidation number that would go along with every atom there, and then we can compare the reactant side to the product side and see if there was a change in oxidation number that would help us identify something as either being oxidized or reduced. Now, these orders are, for the most part, meant to be applied in order, so because they build on each other. So this, just like your solubility rules we talked about earlier, you kind of need to be able to apply these to a situation that will pop up. And we'll see some examples, but again, think about that as you're practicing, right? Can you do this without having to refer back to the rules here? So any pure element, oxidation number is 0. For any monoatomic ion, so an ion made up of just one atom, whether it's a cation or an anion, the oxidation number is the charge. Right? So Cl-, which is a chloride, would have an oxidation number of -1. Magnesium cation, which has a +2 charge, would have an oxidation number of +2. Okay, that should be pretty well established from what we've talked about in terms of ionic compounds. Okay, when in a compound, fluorine has an oxidation number of -1. Right? When it's an anion, we know it's -1, but this would be in a covalent compound where we don't have the metal charge to compare against. Fluorine always gets to be -1. Now, number 4, when in a compound, the oxidation number of oxygen is -2. Right? That's the same as in an ionic compound, but unless connected to fluorine. Right? So connect oxygen to fluorine. Fluorine gets to be -1 first. Right? Rule number 3 is applied before rule number 4. And that might mean we have to figure out what the charge on the oxygen would be. So that's kind of a rare case, but something to watch out for. Now, the other things with oxygen, there are some kind of more exotic forms of oxygen, like peroxide, where you have 2 oxygens with a -2 spread over the whole thing. So each oxygen would be -1. Or superoxide, where you have 2 oxygens with a -1 charge spread over the whole thing, right, which kind of means each oxygen is about a half of a negative charge. We are not going to go into the specifics of those types of compounds here. So for our cases, if you see an oxygen, it's either an element, it's -2, or it's connected to fluorine. Things could get a little more complicated, and we'll see that when we get to the last rule, how we would deal with a situation like that. Okay. Chlorine, bromine, iodine, they have oxidation number -1 if they are in a compound, okay? Unless there's fluorine or oxygen around. So we've seen lots of polyatomic ions where chlorine, bromine, or iodine are connected to a bunch of oxygens. In that case, the oxygen gets to be -2 first. That will mean the chlorine or the bromine or the iodine are going to end up having a positive oxidation number. And again, we'll see that in number 7. Okay, and then number 6, oxidation number of hydrogen is +1 in most compounds. Okay? The exception is when hydrogen is in a binary compound with a metal. Right? We've seen this as hydride or H-. Right? In that case, hydrogen has a -1 oxidation number. It would be the same as its charge. But if hydrogen's not connected to a metal, if it's connected with other nonmetals in a covalent compound or in a polyatomic ion, its charge is going to be +1. Okay, now every other element will fall under number 7. The algebraic sum of the oxidation numbers for atoms in a neutral compound must be 0. So if we know some of the oxidation numbers, like if we know the oxygens and the hydrogens, the other atom in there will have to be whatever would cause that algebraic sum to end up equal to 0. For an ion, right, any polyatomic ion, the oxidation numbers are going to add up to whatever that charge is, right? So if we're looking at something like a sulfate with a -2 charge, well, the oxidation numbers aren't going to add up to -1, they're going to add up to -2, right? But applying those rules, we can figure out the oxidation number that goes with any atom in any compound that we might encounter. Okay, now we want to try this out on a few atoms. So we've got some time. We can just do some practice here with a couple compounds. Then we'll try to apply this to a reaction. So Al2O3, that's just an ionic compound. We should be fairly familiar with that. This is aluminum cations. So the aluminum here has a charge of +3. That means its oxidation number is +3. Oxygen here is in the oxide form. So that means it is in its anionic form as well, -2 charge. Okay. H3PO4, that's a covalent compound. Those are all nonmetals. So we've got to apply our rules sequentially here. So the first rule would be oxygen. Oxygen gets to be -2. Now what I'm going to do here, and this is the way I like to do it, there's not really a convention here, but I like to put the oxidation number below the atom in the formula, and then keep track of the totals above. And we'll see the utility of this when we get to an equation. But if each oxygen is -2, which is what our rule tells us, but there's 4 oxygens, it means that oxygens are they are adding -8 to the algebraic sum of oxidation numbers. The next rule would be hydrogen. Hydrogen is +1 in terms of its oxidation number, but there's 3 hydrogens, so hydrogen is contributing a total of +3. Now across the top, right, that would have to equal 0. +3 then adding whatever phosphorus is, minus 8 would have to equal 0. So phosphorus here is going to have to be plus 5. Now in this case, the plus 5 would go on the top and the bottom because that would be the oxidation number of the phosphorus in that compound, right? That's where the algebraic sum is going to come in to get that last charge on phosphorus. Okay, we will stop right there. We'll pick up the other three in the next video.